Hi, sir. So, my name is Iswaran, and I will be presenting about my mini project is on AGV path planning. So, this project focuses on simulating how an automated guided vehicle, which is AGV, navigates efficiently using a path finding algorithm. So, moving on to next slide is about presentation outline. So this presentation outline, what it consists of is introduction, problem description, objective, system design, methodology, flowchart, and coding explanation. So the next slide is about introduction. Introduction is about this AGV is a robot, considered as a robot used for transporting materials in industries. So it helps improve efficiency and reduce manual work. In modern systems, AGV require intelligent path planning to move safely and avoid obstacles. Okay, next slide is about problem description. So the problem we are attaining is the path for the AGV is fixed, and AGV couldn't be avoiding some obstacles. So if an obstacle blocks the path, the AGV stops, and manual intervention such as human or any else help will be needed for the AGV to continue its uh, journey. So this increases delay and affects production. As I as you don't know means I am working in an industry. So whereas I have seen many AGV having this issue. So to reduce this problem, we need an intelligent system and automatically find a new path. So whereas it can detect the obstacles in the real time, compute an optimal alternative path, safely reach the winding process station, which is our next station, which AGV need to be go, and also minimize travel distance and delay. Okay, next slide is about objective. Objective is about develop a simulation where an AGV can move from a starting point to a goal position. So what obstacles in the environment, find the shortest and most efficient path to reach the goal point. Next slide is about system design. So this system design is uses a grid-based environment where can reach sorry where each cell represents a position. A value of 0 means it's a free path, and also the 1 represents an obstacle. The AGV moves step by step from the start to the goal point through these varied cells. Next slide is about methodology. Methodology is about first the grid, the start and goal positions are defined. So we need to initialize the grid environment. Then a path finding algorithm is applied. So the algorithm will be applied is the algorithm I'm using is BFS. So and then the AGV explores possible paths, which means where the obstacles having, which means the one, so should be eliminated, should be avoided, and then find the zero will be correct, the AGV to find the reaching point. So this AGV will avoid obstacles, select the most efficient route. So the system outputs the path as coordinates. the general path, final path as a sequence of coordinates. Next slide is about a flow chart. So this flow chart shows how the algorithm really works. So first of all, it introduction it's introducing to the code. So this Python code simulates an AGV navigating in a grid environment using the breadth first search, the algorithm BFS, to find the shortest path from a start point to a goal point. And then it's set up a grid. So it will define the grid. In this grid, 0 represents a free path, 0 represents a free path, and 1 represents the obstacles, the place which should be avoided. So from the start, the process begins at the start point, which is here, the start point, and moving into the initialize, the grid, start and goal. So the system initializes the grid environment along with the start and goal positions, and then add start to queue. The start position is added to the queue, which is used to manage the nodes during the search. So along the search, it will manage the nodes and take node from queue. The system takes the first node from the queue for processing. So we'll start take the node for the processing, and then will be asked by a question, is queue empty? It checks whether the queue is empty. If it is empty, the process stops because no path is found. So if it's yes, sorry, before it goes to the AS, is it goal? So it will be find the goal or not. If the current node is the goal, the algorithm stops searching. And then backtrack path is about the system then backtracks using stored parent nodes to generate the shortest path. So it will be check neighbors. If the current node is not the goal, the system check its neighboring cells, which means where it's valid and available to go. And then it will check the valid check. It verifies whether each neighbor is valid, meaning it is inside the grid, not an obstacle, and not already visited. And then goes to the add to queue mark visited. If valid means the neighbor is added to the queue and marked as visited. And it repeat because this process repeats until the goal is reached or all possible nodes are explored. It will be in loop, and finally goes to the AND part. Finally, the algorithm outputs the shortest path from the start to the goal. So next is about coding and explanation. Okay, this coding and explanation, first we define the grid. Before we define the grid, I want to tell you about this import DQ. So DQ is something is like double-ended queue is used for efficient BFS traversal, first in, first out. And then we define the grid. In this grid, 0 represents, that it's a free path, and then 1 represents the obstacle. So the AGV can only move through cells that value 0. So if 0 means it can be moved, if it will be attacked by 1 means it will be stops and will define, and and it will be find the valid uh, point to go. So okay, I'm sorry. So 0 is top left corner, a starting point. So starting point, where is the starting point? And 4 4 is a goal point, is a bottom right corner, final destination. So next, the grid size. We calculate the number of rows and columns using the length of the grid. This helped ensure that the AGV stays with the boundaries. So for now, the rows, the number of rows is 5 and columns also 5. And then applying a BFS function. It's defined a function called BFS, which is used to find the shortest path, from the start to the goal. So its Q means stores nodes to explore. Visited means keep track of visitor cells, and parent were the store's previous node for path reconstruction. Okay. Then the visitor at start node is added first, while Q it will be in loop and stop searching when goal is reached. So this is how the BFS algorithm works. And then moving to next is calculate the next position. Calculate the next position. So inside this function, we initialize a queue using DQ to store nodes to explore. We also use a visitor set to keep track of visitor cells and a parent dictionary to store the path. And also it used the FIFO principle to continue the loop. And then it finds the goal check. If the current node is equal to the goal, the search stops. So here, this part, I'm sorry, this part, down 1 0, up 1, negative 1 0, and right 1 0 1. It's calculating the next position. Mainly, it's neighbor, exploring the neighbor location. So this algorithm then checks the neighboring cells in 4 directions: up, down, left, and right. And then this, it checks the valid move check. For each neighbor, it checks the position is inside the grid, not an obstacle and not already visited. And then it's also reconstruct the path. So once the goal is reached, the algorithm reconstructs the path by tracing back from the goal to the start using the parent dictionary. And then final output, the path is reversed to show the correct order from start to goal, and the result is printed as a sequence of coordinates. And then we will be getting a result where this uh, AGV, where it can go through. So it is clear that obstacles significantly influence the path selection. So instead of taking a direct route, the AGV adjusts its movement to avoid block cells, ensuring safe navigation. So this reflects how real AGV systems operate in an industrial environment where obstacles may be present. The performance of this system depends on the grid size and complexity. So overall, this simulation highlights the importance of path planning algorithms in automation and provides a basic understanding of how AGVs operate efficiently in smart manufacturing systems. So again, before I go to the next slide, I want to highlight this. 00 means it's a starting point, and where the 44 it's end point. So here we get that it tells that we already reached the correct location, which is using the BFS algorithm. It finds the correct location where AGV can be travel on, where it can be go along the journey using this path. So here I want to show you the real simulations of how does it happens when I run I run the module. Okay, so the chosen locations is 00, 10, 20, 30, and until 44, where it reaches the goal point. Moving to conclusion, BFX is effective for AGV path planning, where it can be advisable. So this simulation reflects real world AGV behavior, useful for understanding automation in smart factories.